Hi, this is Ben Lavasani from National Instruments Applications Engineering, and I'm going to give you a brief overview of a project I've been working on along with my colleagues. We built an interactive showcase of NI products in hope to exhibit the wide range of NI products and technologies in the demonstration of an automated and interactive industrial building. This is a small model of an industrial plant where we put technologies inside and made it interactive so you can explore some of our products. I'm just going to give you a system overview now. So we had various rooms inside the plant. We start off with the power generation and monitoring, where we use the cRIO and the FPGA to control a DC motor. Then we use the LabVIEW real-time and the scan engine to do some PID control of a furnace to keep the furnace at a set point. To control the motion of the lift, we use the FPGA to send signals to the stepper motor driver. Finally, we did some load cell monitoring using the DAQmx driver along with a USB data acquisition device. In the next few minutes I will detail which of the National Instruments products and technologies we used for this structure and demonstrate how it became automated and interactive. We used the scan mode with a digital I/O module to send PWM signals to our temperature controlled furnace. A light bulb would increase the temperature of the furnace and a fan was used to decrease the temperature. Closing the loop on this control was a thermocouple input. The outputs were all set using a tuned PID algorithm. In the power generation and monitoring section of the plant, we generate power and distribute it towards lighting the building. This was done by coupling together two DC motors, one powering and one generating. The generating DC motor was used to light the white LEDs in the plant. If the generation falls under 35%, then the red LEDs were designed to flash to alarm that this event had happened. The scales were monitored from the host machine running Windows. We used the DAQmx driver and a USB data acquisition device, which included a C-series module. This C-series module was designed for load cell measurements. This measurement could have also been added to the cRIO, however this shows the tight integration between the different platforms. In the lift section of the plant we utilised the FPGA with a single C-series digital module. This digital module was used to send commands to the stepper motor drive, telling the stepper motor drive which direction and which speed to travel in. We also closed the loop using limit switches so we knew which position the lift was in. The user interface is made up of the following components. We have the security tab where we can override a key lock with a password and also allow us to emergency stop the plant. We have the plant status where we can monitor what's going on in each individual room of the plant. We have the generator where we can adjust the power that's being generated and also do some monitoring on the power. The furnace allows us to control the temperature of the furnace by setting set points. Also we can adjust and tweak the PID on the fly from here. The lift room allows us to cool the lift and monitor where it is in its position. And then finally the scales allows us to observe what mass is loaded onto the scales. The key lock, when turned on, will trigger the software to lock all tabs and immediately switch to the security tab. This is where the operator can either unlock the key lock or insert a password to override the front panel. An additional feature we implemented in the plant was the emergency stop button. This was used to seize the operation of the whole plant and exit all programs when pressed. We predominantly based our project on our embedded cRIO platform. cRIO is a high-performance programmable automation controller, or PAC, that is differentiated from PLCs or traditional type control devices by having a field programmable gate array at the heart of its architecture. For a motion demonstration we use a C-series module for cRIO with a DC motor for the power generation and also a separate drive and stepper motor for the lift. Some basic electronics and mechanics had to be produced as well in order to implement our temperature control and integrate our motors with our moving parts. Finally, the integration between our user interface on the laptop and the plant itself also involved USB-DAQ with one of the C-series modules. This measurement was implemented using a single sleeve carrier chassis for C-series modules. However, this could easily be implemented to take wireless measurements using a Wi-Fi DAQ. The tool that brings all of these together, of course, is a graphical system design environment that is LabVIEW. To use LabVIEW and control the compact cRIO system, we use LabVIEW real-time and FPGA modules. Traditionally, FPGA use has been restricted to hardware design engineers who are experts in VHDL, the description language that will define how this chip behaves. However, LabVIEW enables you to benefit from FPGAs without having to learn how to program in VHDL. Compact cRIO is entirely programmable with LabVIEW graphical programming, including the FPGA, the real-time operating system, and the human-machine interface. We decided on the compact cRIO for its real-time processor, reconfigurable FPGA, and C-series I/O modules. The real-time processor was great for deterministic and standalone operation. The FPGA was used for high-speed and custom I/O timing, triggering, and control, and the C-series modules allowed us to connect directly to our signals with onboard signal conditioning. The scan mode is a new tool within LabVIEW 8.6. Using the scan mode, you can choose between accessing each I/O module directly in LabVIEW real-time with no FPGA programming. This was an extremely beneficial and educational team project due to its modularity. It involved a good hardware and software balance, and we even got a chance to experience the system engineering process, from requirements documents all the way through to deployment of our project. Of course, this was all done using LabVIEW. The most obvious application for this combination of technologies is building control, such as a smart building. However, now consider an automotive plant in car manufacture. It needs security features, power generation and monitoring, for example in the production of hybrid cars. Finally, temperature control could be used to keep the environment at a desired temperature for painting cars. At the same time, a lot of these principles are used within other industrial plants, such as food production, process engineering, chemical plants. As well as all of the above, this would be a great project to give to students. It's modular, so it allows students to be able to go away and work at their own aspects of the projects, and then the integration of all of these modules will really show good teamwork. Thank you for watching our video on the measurement plant. Hopefully you can see some of the benefits of using National Instruments hardware along with LabVIEW graphical programming for your future projects.